And of course, I need to connect to the screen here. Yes. Perfect. Better. Much better. Yes. I have structured this class in two parts. First, we do kind of recap and finish the topic of fuzzy logic, because it was a brief introduction last time. So now I want to put it in the context of one more or less concrete application. And based on this application, so we recall the main principles of fuzzy logic. Why do we bother at all with it? And this will happen in the first half of the class. And in the second half of the class, so we move on towards a new type of reasoning. So we will spend a little bit of time talking about what kind of reasoning we consider so far when talking about classical logics. And which is kind of looking a little bit ahead, belongs to a class of non-monotonic reasoning with closed-world model. So, and we move on to a new type of reasoning where we use a so-called open-world model. And the reasoning in the open world model is opposite to non-monotonic, is called monotonic. And move on with a specific use case of monotonic logic, a technology that uses this type of reasoning, which is called semantic web. Right, but first thing first. So let me just see if I can remove this thing from the screen like this. Yes. Fuzzy logic. Before we're going into really the fuzzy logic, I last class we ended kind of open-ended with a statement that fuzzy logic finds its application, main application, in the context of automatic control. So what is control and why fuzzy logic makes sense in this context? So automatic control. So in general, we are talking about a system that we can interact with. So it's a system in its general sense. And we are able to interact with the system and affect its behavior. And so by doing this, by applying certain interaction signal or interaction or activation, we change the behavior. And this system can also be monitored somehow. So we can observe changes somehow. And our task in this case is to automate the interaction for having in mind certain objective functions, so that we also have some reference behavior in mind. So what does it mean? So what is this system that we can interact with and control its behaviors? For example, what do we have here? Like these guys, like thermostats. So measuring temperature, or I think those are just mechanical stuff, the thermostats, but thermostats. So they measure a temperature. Moreover, we want to maintain, for example, a certain temperature in the room. So we have in mind the behavior of a system that maintains certain climate in the room. And how we maintain the climate is on a certain reference level is by interacting with heating elements. So we either can turn them on or turn them off. Okay, I will not go into the details of control theory. In many practical cases, we don't want to have it like on-off type of control. So we have rather continuous range of changes, and then through these changes we affect the system that we interact with. Right. And so in automatic control, as I said, so we are interested in building a system that do this job of maintaining certain reference behavior of the target system in an automatic way. And this is done, so we need to complement this figure with this couple of extra blocks. So this observe changes, so we do via kind of measurement system or measurement block. Sensors. Of some kind. And these sensors are then fed into, so now we need to precise this actuator control signal. So that would be a block, which in the context of AI normally referred to as actuator, but in the classical control terms, this block is referred to as controller. So the controller takes two inputs and outputs a control signal. So this interaction signal that goes into the system. So it takes this reference behavior and takes the measurements of the effect of the changes, which is also known as error. And here again, so I'm presenting it on a very, very high superficial level of details, but this is a main idea. So I just want to go quickly to the actual problem. So in the classical control, automatic control or control theory, so this controlling is done on exact computations, based on exact computations, meaning that you feed in values. So for example, a temperature. So on exact computations. So so exact computations here means that you need to have a model of a function or mathematical model that of parameters that you actually observe and are used to compute what would be the output signal. And to do that, this model needs to reflect the phenomenon that you actually want to that you interact with. And here we are talking about controlling a behavior of a system over time. And it means that the mathematical model often comes in form of differential equations. So how a system reacts in time on certain based on certain inputs. But in general, we are talking about mathematical model of so this target system dynamics. So basically, applying something will result in some changes of a system over time. And then there are actually, and this mathematical formulation allows actually to do computations that, for example, can compensate for errors. So you observe an error, and you know that how the interaction system should be changed in order to have predictable behavior of a system that approaches asymptotically to the reference behavior that we have. And here we come to one of the problems or challenges of classical control which is actually the complexity of coming up with this model of a system. So in many complex cases, so if you take a complex industrial plant, coming up with exact model of a system is very difficult. Sometimes it's even impossible. So so if you would take control course from our control group, then you will see all the possible procedures they do to overcome this difficulty. However, here we come to the place where fuzzy logic can help us. Now I want to sketch in what way. So essentially, so we will replace the need for the exact model of a plant by fuzzy rules. So we will create a rule based on some expert knowledge about how the system should be controlled. And by the way, looking a little bit ahead, so this controllers exist in reality, and I think the peak of the development was back in the end of 1980s. So with several real-world systems being developed, like controlling subway stations and subway trains in Japan, improving autofocus functionality. So nowadays, I think they do some machine learning-based autofocusing. So, but it was quite an advancement once upon a time when they used fuzzy logic for getting a better quality picture. So what do we do? So we will focus now on this part, and we will replace it with the fuzzy logic. And why? So there are several advantages, again, looking a little bit ahead. So if you would create such a system, first of all, it becomes very explainable. So because the necessary part of the system, and you have this diagram in the slides, are the rules. So these are the rules over so-called linguistic variables that we introduced last time. So you can read the rules, and it is intuitively clear. So how do you control a system? Secondly, you can easily update this set of rules if needed, and not only set of rules, but also associated fuzzy sets. So now again, we will come back as part of recapitulation. And this is one of the problems with the classical control. So for example, if once you created a model, then it is kind of fixed for the duration of the system. So updating the model, it is yet another challenge. So fuzzy controller then has the following structure. So if we have this controller, so it takes in this input signal, so the error. Then it has, as you remember, fuzzifier block. Then we need to have knowledge base or rule base. So let me see if we have to mute somebody. So we need to have a rule base that actually reflection of the control procedure, and inference block, and finally defuzzifier. And that's what we will very, very quickly. So again, so not stopping on the details. I will now recall, and then the output of this is again it's precise value or crisp. Of the effect of the of the control signal that goes into the system, and then via measurement system fed back into the controller again. So fuzzification. So three steps: fuzzification, rules, or four rules, inference, and defuzzifier. So for the fuzzification, we introduced a notion of fuzzy set. And fuzzy set in itself includes two parts. So it's a linguistic term or variable and membership function terms membership functions. So linguistic terms, for example, a fuzzy set for temperature that we started to talk about. So terms could be, say, normal and hot. And to define the fuzzy set, so you need to define a range of possible values. So say from 0 to 100. And then you need to define a membership function. And membership function for temperature or for any linguistic term is always bounded between 0 and 1. And then you make a certain assumption on how this membership function should look like. So, for example, if we have 100, so then we have probably 80 here, and maybe 90 here. So that's hot. And normal, then it can be, well, it's depending again. So normal, I will explain why it can be normal. So normal again. Normal can be also have the same shape, and they may intersect, overlap between the linguistic variables. Again, the names, the chosen names, it really depends on the use case. So if we talk about climate, then obviously, I mean, something is wrong with this scale. But if we talk, for example, controlling cooker of warm water, then I mean the ranges for definition of normal and hot can be different, of course. Right, and in this way. So we talked about these membership functions that could be different, and they should reflect the phenomena that you try to capture. So and they can be empirical, so that you fit expert opinions, or they can be analytic, like for example, in this case, mu hot could be defined as 1 minus minimum x minus 90 degrees divided by d 1, like this, and d would be this span from the central value to the border of the interval. Yeah, so it's a triangle function, so you can come up with many other functions. But then again, the important thing that you allow for a certain degree of overlap. So when you create a fuzzy set, so that's the key thing that introduces uncertainty of mapping crisp value, which can fall into different categories. So the whole thing is called a fuzzy set. I mean, a collection of linguistic variable with associated membership function is called fuzzy set. Fuzzy rules then, that's easy. So they are they should relate the input and the output side membership functions. So output. Uh, so what do I mean here? So it is type of if-then rules. If something happens in the input, then the output should be this.
Ja, det gick jättebra. Så de ordnade marknaden givetvis där. Det kom.
Det är superbra, det gick jättebra. Mm. All right. All right. Yes, so it is this kind of rules. It is the designer that actually creates them. For example, again, so let's take an example. So we have this, say, a steam turbine, so steam that produces electricity. And we want to control its effect, so production of energy by an actuator, which is, well, in the very simplest case, a single valve connected to it. And then, so this control, we will based on the observations of two variables, temperature and pressure. And again, so if we now express this scenario in linguistic terms, so we need to introduce terms for three entities here: for the temperature, for the pressure, and for the control signal, or for the control variable. So temperature. So let it be T low, T normal, T hot, or the same for pressure, P, or actually that was, sorry, I mixed up a little bit. T normal, hot, very hot. P low, P normal, P high. And then our valve. So valve. So what is it? So we have it's a knob. So we can turn it into to certain degrees. So we we can have it like negative small So we have ranges or negative large. Negative small 0 positive positive small and positive large. So these are our categories. And obviously the function, I will not, well, I will sketch some of them towards the end. But this linguistic term will correspond to intervals of certain degrees of turn between, say, minus certain degree to plus certain degree. And then the fuzzy rules. So, I mean, you can think of it as a table. So you have temperature on the one hand. So T norm, T hot, T very hot. And then the pressure, P low, P high, P normal, P high. And then again, so depending on the combination, so you can have different control signals like positive large, positive large, positive small, 0, 0, negative large, negative large, negative small, negative small. So that's the rules that you may come up with to the system. So, and basically, if you just take one rule, you can spell it out. If temperature is hot and pressure is high, then so hot, high, and then rotate negative small. Rotate wolf. Yeah. And then, of course, this negative small, so it has certain intervals of crisp values. Again, so it's this is the output membership function. So again, so you can think of it as a set of triangular functions. So when you have negative large, negative small, 0, positive small, and positive large. And here is the range of degrees of this controller. So say 90 degrees plus 90 degrees, and this is mu out. So this is the fuzzy set for the control variable. So finally, what is important to complete this story? So we have these rules that map input fuzzy sets into, or instances of fuzzy values into the output fuzzy value. And the task is to first convert the crisp input into fuzzy value, do inference, and then at the end to come up with the crisp output value that is used for control. And that's what we did last time. And just to sketch one instance of such thing. So if you have this membership functions for the temperature, so you, for example, this is hot. And this would be norm. And similarly, so we have mu pressure. Again, so here we have, say, norm. And we have here low. So now, and here is the range, say from, I don't know, to 200 degrees Celsius to 800 degrees Celsius for this turbine. And here we can have again values from 100. What was it? PSI to 1000 for pressure. So now we do put it in motion, and we measure some crisp values at this range. So, for example, 300 degrees. So our sensor reports. So fuzzification means that we consult the fuzzy sets and figure out so what is the outcome. So it can hit, for example, 0.2 of normal and 0.8 of hot. The same here. So, for example, 0.7 of normal. So if we have certain, I don't know, the 400 psi, and again some 0.3 of low. So now what do we see here? We have different alternatives. So this fuzzification give us different outcomes of different instances of the fuzzy set, and it means different rules will be activated. So in this very simple case with two variables, and again, so the case of this particular crisp input. So we have four distinct cases. So so the value can the temperature can be normal, and the temperature can be normal or hot, and the pressure can be also low or normal. So, and now we need to map. So we need to select all the possible cases where this output is applicable. So we need to select these two cases of normal and hot, and low and normal activations over here. And these are, in principle, possible outcomes on the output fuzzy set. So we can, so the action will be somewhere in between. And to do this, we need to do kind of we need to do aggregation. So this is the main difference from the classical logic. So we use several rules at once. So whatever applicable, and then we need to perform a step which is called aggregation. Aggregation of rules and outputs. So what does it mean? So this input should be considered together now with the output set, and the output set may look like this. So we would have say a 0 activation, 0, and connected to it positive large. So in between we have positive small. But I mean, we are not concerned as this is not part of our output. Yeah. So here we simply map. So we apply this for different rules for different and use this scores to reflect the area of the activation. So here it will be like 0.2, 0.8. So one rule says that, okay, so you should look here. So for normal, you need to activate, for normal, you activate, you do 0 activation. Right. And 0 activation also for hot and normal. Hot and normal and normal. So normal. So you have a 0 activation. So and you have two different possibilities. So the rule for the pressure produces a larger score. So and so you need to choose one of the most applicable rules. And again, so there are normally strategies. So it's when it really depends on the design. So normally, normally, you can use OR as the aggregation strategy. So meaning that you choose the maximum score. So, and in this case, so it will be this area over here. And the same goes for the other parts. So where we have hot and low, I guess. So hot and low. So in this case, we need to choose positive low. So again, you choose the one that has a higher score. So here we consider the hot with 0.8 score and low, which is 0.3 for this input value. And that would be, again, so something like that. Okay, so and now you need to do the final step, which is dephasification. And for dephasification, so you basically take, so you need to compute. You need to compute a common value for all activated areas, and there are different ways of doing that. So you can use you can compute mean value somehow. So you compute the areas and take the mean, or you can take a minimum value of the activated or the maximum. One of the common ways of computing this or mapping to decreased values to compute center of gravity. COG. So which may end up somewhere here, for example. And then you basically compute the corresponding X value, and that becomes your crisp output. So, and in this way, so you may design very complicated controllers, as I said, so they will be flexible in terms of updating this model. On the other hand, so the main drawback is that it's really expert specific, or at least this is highlighted as the main drawback of fuzzy logic controllers. So this is it. Fuzzy logic control. Any questions? So concrete application. What is again? So important again in especially in the AI context. So when we deal with the environment which we cannot probably model in advance. So this is one of the mathematically sound and logically sound way of actuating, performing actions on the environment. Okay, so let's now take a short break, and then we swap the topic, and we enter into this area of monotonic reasoning. So 5 minutes break. In 22:04 we listen.
Så hur är det bara är det som multiple choice question eller är det att vi ska skriva det?
Det är olika. Jo, men det är multiple choice, de flesta.
Hur många försök?
Ja, försök. Nej, men det är inte rocket science. Jag kan lova. Och som sagt, jag testar grundläggande förståelse av de koncept som vi har gått igenom. Så logik, lite resonemang, CNF, första order logic. Men igen begränsat till det som vi har gått igenom i klassen mer eller mindre. Och som ni ser i boken.
Det är svårare att vi skulle göra diskret matematik.
Nej, jag skulle inte säga det. Nej, jag skulle inte påstå. Så, som sagt, så för mig är det ett sätt att, och det, igen, så ni kan använda boken. Så syftet med quizen är att inte stressa er utan att bara testa att ni får er med materialet.
Hade du kollat hur lång tid vi hade på oss att göra quizet?
Just nu så jag kan figurera det med 2 timmar.
Och det var.
Ja. Okay, so now we move to av någon anledning jag ser inte det här på skärmen. Mm. Just. Okay, so let's switch to more PowerPoint mode. So we will be talking. So we are starting the next module. So in this module, we will be talking about technologies, tools, which were invented and developed in the context of so-called semantic web. And I specifically, I want to be kind of explicit and clear here. We learn it because the technologies are still in use for describing represented knowledge, doing reasoning. There exist ontologies, comprehensive ontologies or knowledge bases, basically, for specific domains in medicine and genomics and many, many others. Semantic web, however, doesn't exist, and it was one of this big technological failures at the end. But again, there are good reasons for that. So probably the world wasn't ready in full. There are different reasons. We will be talking about them even today. But we come to the main idea that I kind of articulated already during the first class. We want to automate reasoning, so we want to create software that not executes executes fixed set of commands, but relies on information that's kind of stored separately from the execution logic, and use this information or knowledge to plan the next execution step. And here we enter into 2 cases. So the first one that we have considered implicitly or even explicitly, I mentioned it, is the case where we have kind of a complete knowledge about the environment that we are that we want to reason about. So about the world. world. So all the facts exist in the knowledge base, and we do reasoning. So our reasoning outcomes are based only on this information that exists in the knowledge base. And the second obvious case is that when we don't have such assumptions. So we explicitly assume that there might be knowledge that doesn't exist in the current at the current moment in the knowledge base. So the first case that's actually applicable to classical logics and system based on classical logics is the case for non-monotonic logic. And as I said, so you only make statements and judgments about or using the facts that exist in your knowledge base. So if something is not explicitly stated, then it is false. So as exemplified here. And this this is called the closed world assumption, which is behind classical relational databases and expert systems, all the expert systems. In this case, so if some new fact appears, so you need to do revision of your rules and facts, because some new facts may come in contradiction to what you know about the environment before. And so typical action or functionality for this type of systems is that you should do belief revision. Yes. And non-monotonic logic, again, so it does reasoning only within the context of the facts that exist. So you do revisions, and then you basically your reasoning is conserved within the facts you know about the world. And when you discover some new facts, so you, for example, as exemplified here, so you change your skills, you obtain new skills when you grow up and go through different educational steps. So these new facts definitely invalidate some old facts about yourself. So that's what I meant by the need for revision. That's what I mean. The practical systems involve mapping of the phenomena that you model into one of the logics available. So you can, so for example, if you have a story describing certain relationship between actors in the world, so you can formalize it with some atomic statements, and then you can construct rules. So we will not go through all these details. So this PDF will be available, so you can trace this example yourself. And then what we can do, so we have some starting point normally, so for the reasoning, so the current state of the system, that's for example, so let me just remove. No. That can be described by this logic, this formula. And then you consult your database of available rules, pretty much as we did with this tiny example, but it can be as complicated as possible. And derive new facts. But again, so all these new facts are conserved within the rules existing in the knowledge base. But then you can see how. I mean, so the inference is about discovering, so for a given initial state, discovering what it converges to. So what so you can so applying certain set of rules applicable to the initial state. So you come up with a new formula, and then you consult this formula and find new applicable rules. Normally, well, I will come to this slide later on. So you construct kind of tree of all possible rules applicable, and then perform a tree search on it. And in several steps, so you basically come up with a terminal state when no rules are applicable to your state, and you can try interpreting again in the context of that story that we tried to model. So this is again what we can do. What we can do with non-monotonic reasoning. So again, so you can so having this database, so you can query it with different initial states, and again, so it will give you interpretation. So what does it mean? So and practically, so you construct this distributed tree, which you navigate to find the termination state. So now, as I said, we move into a new domain, and we want to focus on systems of a very, very large scale. So meaning that the information that we are talking about is of the scale of the World Wide Web. So it's like lots of information that we want to reason about. And such systems we call open systems. And so what we can assume here is that if some information doesn't exist, it doesn't mean that it is false. So it may be, I mean, eventually it will come along. So, and this is the core of the open world assumption. So everything is allowed, if not explicitly prohibited, and which is behind monotonic logic. So we again apply logical reasoning, but under this assumption that we cannot assume anything if it is not part of our database. And again, so what is the difference about monotonic reasoning? It's like a discovery-driven process. So you start with some input, and then you complete the white spaces. So consulting the knowledge base that you have. As you will see later, so you will see some practical examples later on in this module. So, and in this case, so you need, I mean, when you cannot do obviously the belief revision here, because I mean you have this open world assumption from the beginning, and in this case you need to tag certain information about its validity, and so in this way you introduce the time aspect. So, and we will consider this type of reasoning again in the context of interacting systems, IT systems, with heterogeneous components. So exactly what we have today. So we have users, human users, we have informational resources, home pages, or whatever pages we have, the web services that talk to each other. We have physical mechanisms that also use some information, etc., etc. And all of them need to communicate and exchange knowledge and reason about it. And so the system, again, so what I'm showing you now, it was exactly the motivation, the starting, the selling point for what later on became semantic web technology. So the idea was to create a really smooth engineering framework, which is applicable for different categories of users, for administrators and users somehow. And there are two kind of starting fundamental starting points. So you first you look at the environment, or you consider the environment as I mean, from the standpoints of your needs. So you as a user, well, you as a human, but any actor using this technology should have a notion of a need. So I have a need in doing something, and I want to understand how can I apply certain functionality for my purposes. And so this has the second side of the coin, is that I mean, if there is a need, then there should be capabilities. So there is a way to describe capabilities, that I'm capable of doing this, and that. And so basically matching the needs to capabilities, so that is what you're aiming at. Capability, and again, so here we come to complexity of the task. So the needs and the capabilities, so they for similar objects, or similarly similar objects, so that they're different depending on the context. So for example, so in the context of a service of the car having some basic capabilities would be expanded with capabilities of giving a ride to customers. And another fundamental definition here is the definition of agent. So we talked about agents or intelligent agents in the very beginning of the course. But here we are talking about more concrete virtual representative of every resource that wants to communicate in this context. So this resource should have attachment to the physical entity. They should be able to communicate. So it means that there should be some communication environment and protocols to exchange the information. And semantics. So there should be some common representation of the knowledge to be exchanged. So semantics. So we come to this word, which is actually extremely overloaded and used differently in different contexts. So previously, when talking about classical logics, we talked about semantics as definition of truth for each statement. So here we expanded somehow. So we talk about meaning of anything. So and here is what we want to achieve at the end. So this simple cartoon to trace. So we have a conversation between two people. So the message of a guy, I love you, and while he has certain things in mind regarding what does it mean being in love, and what does it mean being a wife, for example. I don't know, maybe not in Sweden by default. Nevertheless, this message is communicated, no problem. So we have a communication channel to communicate this. However, again, the problem that there can be different meaning put on this concrete message that is received at the other end. And then the problem is that I mean, this message can be communicated in many different ways, like in synonyms or languages and such. But still, again, the common denominator is some content of what the actual meaning, what is attempted to be conveyed. And in the same case, the messages in a certain format can be received and understood and parsed to the other end. But again, they should be mapped to specific content somehow. And this is the problem. So we have here two different contents for the same messages. So what is how can we achieve this? How this is the problem we try to look at with the second module. So how to communicate the meaning and connect it to certain messages. So in general, this is a hard problem. So how to do this connection? And actually now it's not a big discovery, but nevertheless, I found out that I mean, with respect even to the content of this course, so we are now entering the area where we have this connection or obvious traces of this connection in the case of large language models, so which in principle can be used as this kind of common denominator of mapping of different sentences to meaning. But again, so LLMs are still a kind of black box, and again, as you will learn while reading the paper for the final assignment, it's not yet clear how to this concrete mapping of the say verbal messages or textual messages to actual meaning. So here I'm just trying to highlight the complexity of problem formulation. So we want to connect some textual representation or symbolic representation that is used to communicate certain information to the actual meaning that is that you want to convey. In addition to this, as I said, there are different ways to express the same kind of knowledge. And what was attempted, and that was the core idea, so back in the end of 90s, beginning of 2000s, what was attempted with semantic web is to approach this problem by by explicitly representing meaning and making it available on a global context for communication between different parties. So now the communication between different agents would involve not some loose or baggy formulated messages, but rather well-defined formally described meaning with the reference to the source where this meaning is defined. And this is very helpful for many applications. So when you can do this, so then you can match, for example, your needs versus capabilities of the other entity, and you can and this can further lead to creation of useful services. And we will be talking so starting from today and so until the end of the course in the next maybe 4 classes, we will be talking about the tools. So this behind semantic technology. So tools to represent meanings and knowledge. And see how I mean, what again, how the reasoning is done. So basically separating the execution part from the knowledge representation. And I will do references to semantic web, even as I mentioned already. The technology doesn't exist, but so in this basic course, so we learn it as a really good case study. And again, I put the a reference, or if I not, I will put it online. You can read about analysis of semantic web and why it didn't roll, so to say. So it will be available in Canvas. But the idea was really cool. So first, it was an obvious understanding that there are plenty of information appearing or which appeared in the World Wide Web. So service-oriented architectures already were in place. So web services, so that was kind of all actioning. So, and the question was how to progress World Wide Web to the next level. So when you use all this information for non-obvious reasoning. So, and essentially to transition from web of links to web of meaning. So and again, so to me, this is an open question. So yes, semantic web is not existing. LLMs exist, but still it's in a very early stage. So what will it be at the end? So that's really wondering about. So now we see tendencies, for example, of merging. So for example, search engines and LLMs, so vector databases. So a symbiosis of it. So definitely will exist. But nevertheless, the technologies behind it, like representing knowledge and reasoning about this, they still exist and used practically. So let me just skip a couple of slides. So they exist and used practically. And again, so the whole concept of representing knowledge, it is not new. So it is rather stable. So we are talking about here representing knowledge graphs. So if you can read it about it in the corresponding chapters. So now I can maybe drift a little bit on a side, and this summer I visited my colleagues at University of California, Irvine, and what they did, so they combined knowledge graphs about certain situations with visual transformers. So and the idea is really kind of cool. So they want to do this visual semantic scene analysis. So, for example, you have a video, and you want to understand event of aggression against policemen. So and you want to predict aggression. So depending on the behavior, shoplifting. So you want to be able to see certain patterns to define whether a person did something illegal. Just doing computer vision, so deep learning based analysis, you cannot, I mean, it is very hard. So to train such a network, so in a supervised or unsupervised manner. So what they did as a demonstration, so they extracted these knowledge graphs from LLM. So for example, so they did several iterations of prompt engineering, asking, so define shoplifting. So and then so talking to ChatGPT. So and ChatGPT is really good at outputting structured information, and so you can even so output in a JSON format, basically describing this knowledge graph. So what events or correspond to shoplifting, for example. And then they use this knowledge graph, or basically the labels of this of different actions. For example, like a person looking at the side and at the same time hand is moving on to the shelf. They use these labels to train the transformer. So they extract the objects with the transformer and they do the label matching. And then they do this kind of inference, so similar to one we will look at, to give a score. So how the scene or these objects extracted from the scene correspond to an event of shoplifting, and that actually it works very well. And then you can when you do have this structured knowledge representation in a queryable format, we will look at possible querying languages again. So there can be different, but I mean this is one of the standards, and so they can, for example, embed these knowledge graphs into again visual scene analysis, and ask so for example, if they analyze a scene with fork, pan, and I don't know, a telephone. So which of the items can be used to pick a food from a plate. And apparently, I mean, so essentially, it's not only so the idea is that it's not only fork that can be used, but any item with a sharp end. And then again, so this combination of object detection from computer vision and kind of querying about the properties, so what you can do with these objects. So altogether, they provide very interesting and powerful solutions that otherwise are very difficult, if not impossible, just to achieve with purely with deep learning approach. Yes. So let me see. And what we will do, so now I will wrap up this class, but we will start with very simple tools, which is called a resource description framework, that will be used to make very simple statements about objects in the world. So no relationship yet, and then we gradually kind of make the situation more and more complex. So introducing relationship, partial hierarchies, and such. So we want to create such statements that, for example, Sweden. Well, in pure textual for visualization points. So, for example, Stockholm it just appears as a category. I mean, of the page, but we want to formalize this knowledge and also be able to describe that Sweden has capital and Stockholm has different neighborhoods, and etc. etc. And that is another thing, what's a kind of heritage of semantic web. So the technology is not in use, but it left after itself a set of workable and working standards. So RDF, RDFS, that we will learn, ontologies, all language. So they are still used and for people doing more symbolic AI. So I know, for example, again, I can make a nearby reference to a group at Ericsson that analyzes the logs of 5G cells. And they have a knowledge base describing certain problem cases. And there's no a knowledge base, so they for example, use RDFS language to construct and to navigate and query it. So that's what we will learn in the coming 4 classes. All right, then I finish for today. So any questions? So I'm still here. Yeah.
How much of an object representation is based on that utility? For instance, like if you have 2 forks, that one fork is literally just, it's a golden historical archive, basically. They are both forks, they're not the same thing.
No. We will learn that when we come to talking about ontology. So the question is, I mean, how to describe and differentiate objects based on the utility. We will come to the notion of instances. So you describe. So you have general description of categories, and then you can instantiate them. So I mean, pretty much in the object-oriented manner to make a distinction. And they will be, by doing this, I mean, when doing the reasoning, so they will be treated differently from the fork, which is historical fork, which can be treated differently. So you can do that. I mean,
I'm thinking like the difference between a table and a chair sort of be utility. Like you can use a table. So then how would you make a distinction that, well, this is a table, I need to sit down, can I characterize this table as a chair and use that?
Oh, yeah, but that's a valid comment. There is ambiguity. I mean, so but you can define the property. So so for example, when defining a table, I mean, it can be part of the property of the table. So for example, what you can do with it. So not only to eat, but you can sit on it. So or it's rather opposite. So you can define. That's what probably is the right answer. You can define a property to sit. I mean, to sit. So situation of sitting, sitting something with on a flat surface. I mean, in the kind of first approximation, and then so when doing reasoning, you can match. I mean, against all instances with a flat surface, and infer that you can sit on a table, say. So you don't need to define table as a chair, but rather you approach as part of inference. So so you describe your action. So I want to sit. Then you construct. You consult the description of the act sitting. So the properties of it, and then you select the characteristics of the objects on which you sit and match against whatever you have in your surroundings. Maybe it will be a floor at the end. If that's what you meant. So I think that's what you mean. So it is not about overloading, describing one object as kind of as universal as possible, but rather so you stick to just to its description. So the functionality may change as part of inference. Exactly as I said. So what they did. So for example, they had a description. So What do you need to, for example, pick, a food from from a plate? So you need something sharp, and then you can solve. So what are the instances you have with the sharp end, like that?
In order to define sort of the meaning of an object, is there any other way than sort of reinforcement learning in terms of seeing a result and then
I mean, now you're talking about learning strategy, but you still need somehow. Yeah, of course, you can implement this functionality without conceptualization. So purely so if you don't know anything about categories, so you just do it, you try to see it, it's something sharp, so you reinforce it, next time you don't see it. So you don't know why you don't see it, but I mean, you just know based on your experience. So it's your cost function that tells you. But I mean, here we are approaching it from a slightly different angle. So you kind of you do some reasoning activity. So you make a conscious choice. So and before sitting, so you assess your chances of kind of succeeding. But then you can you can implement certain learning on top, of course, or in parallel rather. So at the end, so AI functionality is about learning conceptualization and learning on and inference on conceptualization data. So all kind of together.
this case, in order for an object to infer other things in sort of, if you imagine a real world setting, then you kind of want to combine an already pre-existing knowledge base with procedural, so that it create based on this end per set, it can then create a ask function, I suppose.